complex number z equals 1 minus 2i is a 0 of, and you know what, I'll stop right here and I'll just say, okay, well, here's what they're trying to see if I'll miss. If 1 minus 2i is there, 1 plus 2i is there, they always come in pairs. Imaginaries are always in pairs. And you can think of it as, you know, the quadratic formula, and having that plus or minus piece in there. We're always going to get two answers. So this is for this fabulous f of x equals 4x to the fourth plus 17x squared plus 14x plus 65. And what I don't want to miss about this is there's no x to the third term. Because if I'm going to do synthetic and I don't put that 0 in there, it's going to be wrong. So what they want us to do is work this down and then see if we can get to the last zeros. And we might need to complete the square in order to get those. So we'll just start with the one they gave us. And we have 4x to the fourth, 0x to the third, 17x squared, 14x, and 65. And you need to space these out because we have this complex number piece that we're going to deal with here. All right, so first things first, we start with that leading coefficient of 4. And we multiply that 1 minus 2i times 4. And we realize when we're inside the box and adding that that's going to give us 4 minus 8i. In fact, I'm even going to alternate colors so things don't start running together here. And that brings us to the first spot where we're going to do a little math off to the side and then come back because we need to figure out what 1 minus 2i times 4 minus 8i is so that we can go to the next step. And with complex numbers, what we do is we just do FOIL. But we know that as we go through, if we have an I squared, it's negative 1. So first times first is 4. Outside times outside is negative 8i. Inside times inside also happens to be negative 8i. And last times last will be plus 16i squared. So a couple of things here. First off, we can put those two middle terms together. And then we have to notice that I squared is supposed to be a negative 1. So it's really going to be 4 minus 16. And that would give us negative 12 minus 16i. So that little bugger is going right here. And we hope for nice things, but the first time through, you generally don't get a lot of nice stuff. And what I mean by that is this first 0, 1 minus 2i, it's going to be a little more difficult. So then we put these two together and we get 5 minus 16i, and it's back to the drawing board over here because we need to know what 1 minus 2i times 5 minus 16i is. So there's our next piece to multiply. First times first, outside times outside, inside times inside, last times last. Realize those two middle terms will come together. And that I squared is negative 1. So we'll really have 5 minus 32, which will be negative 27, minus 26i, which, you know, doesn't thrill us to death too much, but put it up here. So then we add real part to real part here, and that gives us negative 13 minus 26i. And back to the drawing board, because we need to know what's 1 minus 2i times that little monster. Negative 13 minus 26i. So, first times first, outside times outside, inside times inside, last times last. Get that? We go, oh, something good just happened. These are going to cancel out, which is fantastic. So I'm really going to have negative 13 minus 52, which is really good news. Like I said, that's the one that's always nasty. The first imaginary that you do is always going to be the worst. So now, we said if 1 minus 2i is there, 1 plus 2i is going to be there. And we have to continue on with this so that we can get this down to a cubic or a quadratic that's going to be factorable. In this case, I think we're going to get this down to a quadratic. This is the fourth one we started? Yep, we'll get this down to a quadratic. So this won't be quite as nasty. We bring down the 4, we multiply, and we notice, ooh, imaginary parts are disappearing, but 4 plus 4 is 8. So now we're going to distribute the 8. Aha, imaginary part has disappeared again. Distribute again. And fantastic news. So that's where we're at. And this is what we have left. Remainder constant x squared. Looking like so. Did I go too fast? Yes, I'm going. You guys okay? Yeah, I go too fast. Yeah, hang on until I know this. Okay. All right, so now, this is a quadratic. We can use completing the square to get this one. It's actually not going to be too obnoxious. We're just going to go ahead and divide by 4 because we know you have to complete the square when there's a 1 in front of the x squared. We'll move our little 13/4 over. And we will complete the square. What do we need in the box? What do we need? 1. 2 divided by 2 is 1. 1 squared is 1, but I'm not going to write it as 1 over here. I'm going to write it as 4/4. Make our job a little bit easier with the fractions there. So this is x plus 1, quantity squared, equals negative 9/4. What should we do next? Almost. What's that? Subtract the 1. Now that was a lot of math. So sometimes what happens at this point is people just go on to the next problem and they forget there was something we were supposed to do when we started this whole process. Find the remaining zeros. Did that. And write it in its linear factorization. Ooh, that's going to be a whopper. All right. So they gave us 1 minus 2i. So it has to be in that x minus a format. It's going to be x minus 1 minus 2i for the first factor. And from that, we reasoned that 1 plus 2i was a factor. Then we found 2 of our own wonderful answers. X minus negative 1 plus 3/2 I. And I can't fit all this on one line. X minus negative 1 minus 3/2 I. And there it is. The good news is we don't have to prove this by multiplying that all back together. That's the good news. You know, we already went through the process of finding the zeros, and this is it. Now, every once in a while, in your homework, your book does some goofy stuff where they will pull a 2 out from these two factors and different things like that. You don't need to do all of that, you know. The one thing that you might want to do is, if all of these parentheses drive you nuts, is you could distribute this negative and write them all out that way, if you wanted to do that. Because the next step, if we were going to multiply these back together, would be to regroup them anyway. You know, so that'd be the one thing that I would do. But I'm telling you this because when you go into the back and you want to check your answers, every once in a while you're going to look at it and go, why is there a 1/4 out front? And then you're going to notice they don't have the fractions back here. So they're pulling all of that out in the front so that they're not dealing with those fractions right away. It has something to do with how much it was going to cost them to type it into your book. And apparently that saves them money to do that. So just on this one, 43210, how do you feel? If you went slow enough, where do you think you're at? Okay, the numbers are pretty good. Not a lot of 4s, that's for sure. But yeah, that's because it's one of those tedious processes where you have to go very slow and very careful to get through there. So factoring, it just won't go away. You know, every once in a while at lunch, people would talk about how they're in exponential and they have some students that just don't want to factor. They just don't see the use for factoring. And it's like we use it all the way through math. You know, you have to factor. So when we factor with real number coefficients, different things have happened for us. Let f of x be a polynomial function with real coefficients. The linear factorization theorem tells us that we could factor that. And sometimes we look at it and say, well, we're going to need a little help. We're going to have to use the graphing calculator to find at least 1 0 to lead us to where we go using synthetic. But in reality, by completing the square, we're finding these factors as well. So where z sub I, those are complex numbers. We saw that in the last one. Recall, however, that non-real complex numbers occur in those conjugate pairs. And we saw that in the last one. And what we did so that we could make this a little easier to multiply it back together was we regrouped. But they're saying, what if you didn't regroup? You know, what would you see anyway if you didn't regroup that complex number piece? Well, if we had x squared minus a minus bix, and then we had x minus a plus bix, and we went through and did FOIL on this big monster mess, you know, and did first times first, outside times outside, inside times inside, and last times last, we would notice, hey, there's 2 of these middle term things here again. And of course there is. And that's because we're constantly talking about that perfect square trinomial piece. So there's 2 of those. And then in the back, this would give us a nice a squared plus b squared if we multiplied this together right here. So you don't have to regroup is what this is getting at. Boy, does it make the multiplication easier, but you don't have to do the regrouping if you want to do these problems. So the quadratic expression x squared minus 2ax plus a squared plus b squared, whose coefficients are real numbers, is a factor of f of x. Such a quadratic expression with real coefficients but no real zeros is called irreducible over the reals. When we started this class this year, I explained we're going to talk about imaginary numbers. We're not going to do a ton with them. This is kind of a chapter where we do talk about the imaginary numbers, and that's because pre-calculus is supposed to be application, which means real world stuff. And so when we get imaginary answers, that means it can't be done in the real world. So this is the chapter where we touch on that. But at some point we realize, hey, if I know I'm going to get an imaginary answer out of this, I probably shouldn't keep factoring. Why would I bother? I know it's going to be imaginary. So that makes it irreducible over the reals. Factors of polynomials with real coefficients. Every polynomial with real coefficients can be written as the product of linear factors and irreducible quadratic factors, each with real coefficients. So they're saying the realization is, hey, if this is going to give me negative stuff, and I'm supposed to use it in the real world, then I don't want the negative stuff. I'll stop a step before that so that I don't get that imaginary piece. So we've seen that if a polynomial function has real coefficients, then its non-real complex zeros occur in conjugate pairs. Because a polynomial of odd degree has an odd number of zeros, it must have at least one zero that is real. What are they saying? Just making that up. Totally made that up. Let's just say that one of its zeros is x equals 2. In reality, it probably is. If I told you that one of the other zeros that it has is imaginary, what would have to be true about the third zero? It would have to be imaginary. Because it would have to be a real zero, and then an imaginary, and an imaginary, because they come in pairs. You're going to have 4 or 5 questions in your homework about that are just kind of, can this happen? You know, if you've got a cubic, could you have one real answer and one imaginary answer? Well, no, because imaginaries occur in pairs. It would have to be one real answer and 2 imaginary answers. So it's those kind of thinking problems about how those imaginaries always occur in twos. So every polynomial function of odd degree with real coefficients has at least one real zero. It has to. You have 2 imaginaries and 1 real, or you have all 3 are reals. It has to work that way. So just gives us a little bit of insight into what are we trying to find, what do we need to do. This bugger says we're going to factor again. It says write f of x equals 3x to the 5th minus 2x to the 4th plus 6x cubed minus 4x squared minus 24x plus 16. No. As a product of linear, irreducible quadratic factors, each with real coefficients. Notice we have the whole page for this one. Alrighty, so we start with this. And we start by saying, is there a greatest common factor? Is there something that's in all of these that we could pull out? No. Do we know any methods to factor a 6-term polynomial? We got nothing. So where do we go? GC. Got to find at least one nice one to get us started, you know? See if we can find something to get us going. 3x to the 5th minus 2x to the 4th plus 6x to the 3rd minus 4x squared minus 24x plus 16. Oh my gosh, I hope that's in there right. 2x to the 4th plus 6x to the 3rd minus 4x squared. Da, 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 da. I'll try and zoom 6. We need one nice one. That's what we need. One nice one to get us started. So second trace, number 2. Get Blinky over to this left one. Let's see, where is Blinky? Blinky's way down at negative 98. What are you doing down there, Blinky? All right, there, and enter. Anybody recognize that as a nice fraction or a nice something or other? Okay, use that one then. All right, so second trace, number 2. We know that one. 2/3. Okay, just in case things don't work out later, we better see what the other one is. Those two are irrational. They're irrational. Now, if we don't recognize them, it's okay. You know, we'll get them eventually. But my hope is that after we work with the square root of 2 and the square root of 3 enough, that you guys would notice, hey, that's negative square root of 2 and that's positive square root of 2 right there. And we can do synthetic with radicals. We can. We can do synthetic with fractions, which we're going to do right now. We can do it with imaginary. We can do it with radicals. 5, 4, 3, 2, 1, 0. They all there? Are they ever, right? Okay. So, we've got 3, negative 2, 6, negative 4, negative 24, and a 16. Boom. 3 times 2/3.
2.
2. Oh, I like that one.
4.
6 times 2/3 is 4. Oh, I like that one too.
16.
Exactly, negative 16. 2/3 times, remember, it's just, if you're doing it in your head, all you have to do is this, you know, and you look at it and go, wait a minute, 3 will go in there 8 times, 2 times negative 8, negative 16. Oh boy, let's see what we have left. Remainder constant, x squared, x to the 3rd, x to the 4th. Oy. Exactly. You just think, okay, is there a greatest common factor I can pull out? Yes. Now, a little awkward, but it's not a perfect square trinomial. I know that because there's a negative 8 in the back. I have to have x squared times x squared to give me x to the 4th. But do we know of two numbers that multiply to negative 8 and add to 2?
Negative 2 and 4.
Well, those we can solve. I mean, this allows us to keep going. So we'd have x squared minus 2 equals 0. We'd add 2. And there are our plus and minus square roots of 2. This little bad boy is the problem. Right there. The instructions said, write it as the product of linear and irreducible quadratic factors, each with real coefficients. Anything that comes out with imaginary answers, we can't use. So we have to back up and say, well, what's the last thing we could use that did not have quadratics
X squared.
with negatives? And there it is. That's what we'll have to use. So let's start with what we know. Very first one the graphing calculator gave us, what was that? 2/3. Now, we could write that as x minus 2/3, but that's kind of the apprentice level. We don't want the apprentice level. What is it?
3x minus 2.
Exactly. We have our two irrational ones, the square root of 2 and negative square root of 2. So we can write that as x plus the square root of 2 and x minus the square root of 2. But when they say that it has to be linear and irreducible quadratic factors, that's when you have to remember, oh, I can't put the I stuff down there. I've got to back up and do what it was it before the I's started to show up. And that's the x squared plus 4. Like so. If they also said that we could not write this with radicals, could we make that happen easily now? Yeah.
Just put on the X minus
We just back up to these two pieces right here, exactly. They don't, by the way, but there are, again, different professors when you go to college that will say, I don't want to see any radicals, I don't want to see anything with imaginary numbers, so give me the factors that you'll get from that. So that wasn't too bad, right? Not awful. We did harder than that today already. So now, This looks like fun. Extra example, extra. Alrighty, we've got a polynomial function that has the following complex roots. It has a -2, it has 1 plus the square root of 3, and it has 5i. I think it has more than that. Give me another 0 that would have. Look at that last example. Do radicals come by themselves? Do we get just one radical 0? Never. Never. Radicals and imaginaries always come in pairs. So we're going to have to add a 1 minus the square root of 3 to this list also. What degree is this fabulous polynomial? 5th degree. 1, 2, 3, 4, 5. 5 zeros. So, gonna use x plus 2. And then it gets a little messy. But this one is definitely, the radicals are definitely the messier of them. So we'll go ahead and make this x minus 5i and x plus 5i. And then in the back, x minus 1 plus the square root of 3 in parentheses, and x minus 1 minus the square root of 3 in parentheses. Now, just like we did before, much easier to regroup these back to by distributing the negatives. And then putting your parentheses around the x minus 1s. So that'll be our first part of simplifying for this one. X minus 1 times x minus 1, or just thinking x minus 1 squared, x squared minus 2x plus 1. What are we going to get in the back? Minus 3. So this will simplify to x squared minus 2x minus 2. All right, bring back the rest of it. Let's simplify x minus 5i times x plus 5i to all right. What do you get if you simplify that? X squared plus 25. Oh, that's not matching up here. Now we have choices galore for how to do the next step. We could multiply the first two together, just using FOIL, and then multiply that monster times the last one. We could move the little x plus 2 back here and multiply that times x squared minus 2x minus 2, and then distribute the x squared plus 25. It really isn't going to make any difference. It isn't. So let's see. I think what I'll do is I'll go ahead and FOIL these first two. Actually, I'm doing phi-ol to keep them in order because my squareds would be the middle two here for inside times inside. Now, it's okay to do all the distribution at this point. You absolutely could do that. But I always like to have the shorter one in the front. I think it just keeps things more manageable. So I'll put the trinomial in front and the polynomial of 4 terms in the back. Okay, now we're going to have to be really careful because there's a lot to keep track of here. We're going to take x squared times everything back there. Very carefully and write it down. Now I'm going to do something a little different. Because what I'm going to do is I'm going to line these up vertically. There's way too many terms here to keep writing this horizontally anyway. So as I get my new terms, as I take negative 2x times x to the third, I realize that's going to be negative 2x to the fourth. I'm going to line that up right below the other x to the fourth term to make this a little bit easier to finish up. And you take your negative 2x times your 2x squared and get negative 4x to the third. Negative 2x times 25x for negative 50x squared. And negative 2x times 50, negative 100x. Not done, but at least I'm organized. You know, this was the first distribution of x squared. This was the second distribution of negative 2x. And now the last one, again, I'll line them up as I get them. Negative 2 times x cubed is negative 2x cubed. Negative 2 times 2x squared is negative 4x squared. Negative 2 times 25x is minus 50x. And negative 2 times 50 minus 100. It's just an easy way to keep it organized. So now we're going to add going down. So x to the fifth, no x to the fourth. Huh, interesting. 25 minus 4 is 21. 21 minus 2 is 19. 50 minus 50 is 0. So minus 4x squared. Negative 100x, negative 50x. Negative 150x. A little minus 100 in the back. Now this next part is thanks to your homework. Because there are a couple of these in the homework where they do this. They say, okay, here's a second piece, as if that wasn't enough. When we put 0 into this function, we want negative 25 to pop out of it. Well, if we put 0 into ours, we're going to get negative 100. Because it's this last number that's all that's going to be left when you put zeros in there. So what would we have to do to this thing to make this be a negative 25? We have to divide everything by 4 or multiply it by 1/4. Either way, everything's going to need to be divided by 4 to make that happen. So f of x will equal 1/4 x to the 5th plus 19/4 x to the 3rd minus 1 x squared minus 15/4 x minus 25. As if the other stuff we did wasn't enough.
That's
Here's a new
115
glitch.
over 4. That's
150, you mean?
150. So it's 75 over 2.
Thank you. I looked up there and ignored the 0. It's going to happen in your homework. They have a couple of those. So remember, you're just going to do what you normally do and just wait until the very end to manipulate and figure out how to give them the 0 that they want. Sometimes it'll be dividing by something, sometimes it'll be multiplying by something. You know, it just happens what they want for that 0. All right. That is everything. Okay, that's a lot of stuff for this section. So let's just focus on today. Today, we were using factoring to find the linear factorization. We were writing polynomials, and at sometimes we were talking about those irreducible quadratic factors. And writing and making a polynomial have a stated 0. So 4, 3, 2, 1, 0, me on how you feel about the 4 topics. Yeah, I'm not going to see. I knew I was going to see as many 4s on this because it's involved, you know. I think you're perfectly capable of all the algebra skills involved, but do you find if you make that one little mistake, you're toast? Yeah. Yeah, you have to go tortoise method on me here. You have to go slow and sure. You do. Again, there's no new assignment. This is just finishing up yesterday's. And the very first thing we did today is probably the very first thing they'll be doing today. You know, they'll give you an imaginary, a complex number that has both a real and an imaginary part of A plus BI. Where you have to use that and go from there. So that's it.